Anyone who knows me knows that I'm a massive fan of anime waifu and Maple Story. Dude, otters in space, with dinosaurs being a close third. Today I want to take some time to talk about space, specifically the methods that we use to explore it. And just so you stick around to the end of the video, I left all the weird things at the very end. I like to break things down into categories, and with space exploration, we can break it down into two simple ones: rocket ships and telescopes, which gives us this neat little 4-quadrant graph back here. The other two sections being without rocket ships and without telescopes. If you look really closely at it, the things with rocket ships go up. Let's start down here on Earth with land-based telescopes. There's only really two types that we need to be concerned with: optical reflecting telescopes and radio telescopes. Explaining how any of them work in any kind of detail is probably going to be way too long for this video, but I'll try my best as we come across them. The same applies to the other kinds of methods of space exploration. Optical telescopes are probably the ones that you're most familiar with. They range from anything from the telescope in your backyard all the way up to Keck 1 and 2 at Mauna Kea, or the largest optical telescope, the Large Binocular Telescope in Arizona. Optical telescopes were first invented in the 1700s by Sir Isaac Newton. The basic principle of them is that they take in light through their aperture, and that light is reflected on a curved mirror or mirror array that acts as a lens, and then it's either projected into your eyes, a camera, or something that the image can be projected upon. The larger the mirror, the better the image quality, and the further out the telescope can see. The major issue with them is that they require exceptionally clear skies to be useful. If you've ever tried using a telescope on a night that has even the slightest bit of haze to it, you'll know that it's impossible to get a good image of even the moon. As you can imagine, this is a problem for doing scientific research. So the only real solution to this is to get as high as you can. Most large land-based telescopes are built on tops of mountains because they have the clearest skies possible. A telescope built on Everest would probably produce the best picture quality, but that's assuming that it wasn't snowing or, that you could actually breathe up there in order to build it in the first place. Radio telescopes don't suffer from that problem though. But then again, their function and use is vastly different from that of optical telescopes to begin with. The easiest way to understand them is that they are massive radio antennas, or an array of them. There are quite a few things in the universe that make radio waves, aside from that one annoying radio station in your town. Planets, stars, and galaxies are chief among them. Radio telescopes are used to listen in on them and to gather as much data as possible. These are used as the primary method of discovery. Most of them look like giant satellite dishes, but because they're basically antennas, they can come in a number of shapes and sizes. And much like their optical cousins, size is key. The larger the telescope or telescope array, the further out they can listen, and the smaller the frequency resolution that they can listen to. The major issue with them happens to be that they suffer from radio interference. This is why they're usually built far off the beaten path. Examples of them include the 500-meter aperture spherical radio telescope, or FAST, in China, or the Arecibo telescope in Puerto Rico. Or at least it was in Puerto Rico. You probably know it best from the movie Goldeneye. Yeah. It no longer exists anymore. Going up the graph here, this is where we get into space-based lasers. Telescopes. We'll get to lasers later. The basic principle here is the same as that of their ground-based counterparts. You have optical reflecting telescopes, such as Hubble and the James Webb Space Telescope, and a small number of radio telescopes, mostly from Russia. The major benefit to them is that they eliminate all the environmental and location-based issues that land-based telescopes have. Hubble and JWST don't have to peer through the atmosphere to get an image, and space-based radio telescopes don't have to worry about direct interference from your cell phone or bird droppings. This section over here, it's probably the easiest one that doesn't really require a lot of explanation. It's direct exploration. Satellites such as Voyagers 1 and 2, the Mars rovers like Curiosity, Perseverance, and Opportunity, the International Space Station, and the manned missions to the moon from the Apollo program. On a side note here, NASA just launched and completed the first mission of the Artemis program back in November. Its goal is to establish a full-time occupied base on the moon, and it's going to serve as a stopover for further missions to Mars. All of these missions share similar elements to them. collecting environmental data, doing experimental research, and preparing for potential future manned missions. And now we come full circle back down to the Earth. This area on the graph is reserved for things that are more exotic in nature for their observation, or contains a lot of experimental processes that are used to prepare for future endeavors. And since I promised you lasers, there's an ongoing experiment involving the moon. When the Apollo program was still going on, they placed a mirror onto the surface of the moon. And every so often, we fire a laser beam up at it, and we record how long it takes for that laser beam to come back to us. This gives us an accurate calculation of just how far away the moon is from us. This experiment has helped to discover that the moon is drifting away roughly at 3.8 centimeters per year. There is one more bit of space exploration that is occurring here on Earth using lasers. The Laser Interferometer Gravitational Wave Observatory, or LIGO, uses a series of finely tuned lasers to collect data about gravitational waves. These lasers are in such precise locations that intersect with each other that even the slightest bit of interference will cause them to deviate. In 2016, they made the first observation of gravitational waves that matched the predictions for a merger between black holes. Space exploration is a constant endeavor and pushes us forward to develop new technologies and methods of observation. Much like how subscribing to this channel pushes me forward to make more videos that are better for your viewing pleasure. So stick around. The future of space exploration is just right around the corner, and I want to share it with you. Maybe in like 2-ish videos. Anyways, I'll see you next time.